of today by Zhiwei. He will talk from Harvard. He will give a talk on a higher arithmetic Siegel-Weil formula for unitary groups. Zhiwei.
Thank you. Yeah, I would like to thank the organizers for giving me the chance to reintroduce myself to Professor Kudla. We actually met in 2005 in Hangzhou. I don't know if you remember. You gave a mini course in this summer school on Shimura varieties. That was the first time I learned about Shimura varieties. Yeah, and over the years, I mean, whenever I need to learn or relearn theta correspondence, I always go to your papers, and I hopefully now I have a little bit more understanding of theta correspondence. Yeah, so I'm gonna report on joint work with Tony Feng and Wei Zhang. This paper is on the archive. It is about generalization of the Siegel-Weil formula and arithmetic Siegel-Weil formula as proposed by Steve in the function field case. So as I said, I'm basically an amateur in number theory in general and especially in theta correspondence. So my understanding of theta correspondence is extremely naive. So we will be, in this talk, there will be two unitary groups, but let's just start with some general motivation. So let G1, G2 be a dual reductive pair. And bracket G1 and bracket G2, these can mean various things in various contexts. So usually these are, bracket is used to denote the adelic quotients, such as this. But later we will give more geometric models for these G bracket. So anyway, it's some space. It's some space attached to this reductive group G on which we can talk about modular automorphic forms. And theta, the Weil representation and theta series give.
What is your field of definition? Is Q? Is any real, totally real?
This
any
discussion, right now it's any global field.
Any global field. Okay, thanks.
Yeah. Yeah. So theta series give us automorphic forms on this product. Well, sometimes we need to take a metaplectic cover. But more geometrically, and that is, as far as I understand, one of the main points of the Kudla program is to talk about the different incarnations of this theta series in more geometric situation. So these GI bracket may be interpreted as locally symmetric spaces attached to these groups, or they may be interpreted as Shimura varieties, if there is one. So, and in those cases, we have these automorphic forms are no longer functions, but they could be sections of, they could be differential forms on locally symmetric manifolds, or they could be algebraic cycles or cohomology classes. And so today we will concentrate on the function field case, and G bracket will mean the moduli space of Shtukas, which is a function field analog of Shimura varieties. So F is a function field. And our goal is to prove part of the Siegel-Weil formula. So that involves non-singular Fourier coefficients. So I will be more precise soon. Now the motivation is first of all, in the case of function field, compared to number fields, we have more degrees of freedom. So when we talk about Shtukas, there is a variable that's the number of legs, which I will recall. And this number is a new degree of freedom in the case of function field. And this, when there's no leg, this corresponds to the usual algebraic quotient as a set. When there's one leg, this is literally the exact analog of Shimura varieties. But we can have more legs, and these don't yet have number theoretic analogs. So yeah, so we are interested in formulating and trying to prove versions of the Siegel-Weil formula for arbitrary number of legs. And we will see that, analytic side, so the other side of the Siegel-Weil formula will, as expected, will continue this pattern. So for no legs, we will see the value, special value of certain Siegel-Eisenstein series. And in the case of one leg, the arithmetic version, we will see the first derivative of the Eisenstein series. And in general, we will see rth derivative. So if r legs, we will see rth derivative. Okay, so that's the main motivation. We can, in the function field case, we can, we hope to get a richer sequence of Siegel-Weil formulas, starting with the special value and first derivative Eisenstein series, we get all derivatives. Okay, so let me, be more precise and get into some definitions towards stating the main result. So X will be a curve, algebraic curve over a finite field FQ, and always assumed to be smooth and projective, geometrically connected. And F is a function field of X. To define unitary groups, we will fix a double cover of X, and we assume this is unramified. So let me first review the notion of unitary Shtukas. So these will be function field analogs of the kind of abelian varieties classified by unitary Shimura varieties. So, but it's a much more elementary version. It's almost just a linear notion. So let's first just fix notion for what is the Hermitian vector bundle on X prime of rank n. It's just a vector bundle. Let's call it F. I just want to fix the notion of a Hermitian form. For us, a Hermitian form is an isomorphism between this bundle and its conjugate dual. So here, sigma is the non-trivial element, non-trivial involution on X prime over X. And this little check F dual means the Serre dual. So okay. So in other words, okay. So this is a Hermitian form. So it's Hermitian if it satisfies this equation. So that's the definition of Hermitian form. Yeah, in other words, you can think of this as a pairing, perfect pairing between F and a sigma pullback of F valued in not functions, but one forms on the curve. Perfect pairing and Hermitian.
Sorry,
Can't see what you're
we
writing.
can't see your writing anymore.
Oh, yeah, it happens from time to time. Let me, yeah. Thanks for letting me know. And whenever it happens, just tell me. Restart the sharing. Yeah, I maybe this last line wasn't displayed, but yeah, I'm just giving an equivalent definition of Hermitian form on a bundle. Okay, now let's talk about Hermitian or unitary Shtukas. So let's suppose I have some test scheme S. And we are going to define a unitary Shtuka over X prime times S of rank n with legs with R legs. R is any integer, any non-negative integer. And these legs will be points, S points of this double covering curve. A unitary Shtuka with these legs is a chain of vector bundles related by rational maps. So this chain contains R plus 2 members. The first, so F0, F1, Fr, each is equipped with a Hermitian form. Is a Hermitian vector bundle of rank n on X prime times S. Okay, I didn't spell out the kind of parametric, this more family version of Hermitian bundles, but this is easy to guess. S family of Hermitian vector bundles, each of them. And these dotted arrows are elementary modifications. So for example, F0 and F1 differ only at a pair of conjugate points. So they have something, a common sub-bundle, subsheaf. It's called F flat 1/2. That's included in both. And the difference is only at x1 prime and its conjugate point. Both inclusions have co-length 1. Have co-length 1. And it's supported at the respective points, x1 or sigma. These are S points, so co-length 1 supported on the graph of those S points. And this rational map is required to be an isometry, compatible with Hermitian form. So whatever you do at x1 prime completely determines what you have to do at the conjugate point. And such modifications is parameterized by the choice of a hyperplane in the fiber of F0 at x1 prime. So it's parameterized by projective space of dimension n-1. So that's the relationship between F0 and F1, and similarly, each of the neighboring pair of Hermitian bundles. You're free to choose these elementary modifications. And the last step, we have to give an isomorphism between Fr and the Frobenius pullback of F0. So this tau F0 is the pullback that is Frobenius on S, identity on X prime of F0. Okay. The definition is a little complicated, but if we look at the case, S is just spec of F bar. What we are talking about here are a bunch of Hermitian bundles. Well, let's just remember the first one, temporarily forget about the other bundles. It's just a Hermitian bundle that's defined not on the original X prime, but on X prime base changed to K bar. And such that this bundle and its Frobenius pullback. So again, this Frobenius is acting on K bar, is not acting on the curve. They differ at finitely many points. And so the behavior of the zeros and poles at those points are specified, but roughly this is just a weakening of a kind of a isomorphism between a bundle and its Frobenius pullback. We don't require that to be an isomorphism everywhere. We allow some zeros and poles. Okay, so that's the notion of unitary Shtuka. So now we can consider the following moduli problem to any test scheme S. We look at the groupoid of unitary Shtukas of rank n with R lags. Okay, so this is this defines a stack. This turns out to be the Ling-Mumford stack. It's denoted by H-Shtuka un R. So un, because we are talking about unitary Hermitian bundles of rank n, and R is the number of legs. So this stack maps to X prime to the R. This is the lag map, remembering these X1 prime up to XR prime. And we can think of this, when R is 1, we can think of this map, this moduli space together with the map as analogous to Shimura variety, UN, mapping to whatever over whatever ring of integers it is defined. This is the, and this is really very similar because the relative dimension here, this is a smooth. Relative dimension is n-1 times R. And this is a, well, for Shimura variety, so more precisely, it's U1 n-1. Relative dimension is also n-1. Exactly the R equals 1 case. There's a little caveat here is that if we literally work with the definition I gave, when R equals 1, you actually get an empty variety, empty stack, unfortunately. Only for even R's you get something interesting, but one can modify the definition. Can modify the definition to get some interesting Shtuka R for R odd. So one can do this by consider some version with level structure. There's also a much cheaper way of getting some of the cases by modifying the value of the Hermitian form. Basically working with GU when n is odd, you can work with GU rather than U to get non-empty Shtuka R for odd R. Yeah, so the main result I'm talking about will be about even. It's only interesting for even R, at least the version I'm going to state. Okay, so I've introduced this the Riemann stack. It is smooth. The total dimension is as a stack over the base field is n times R. One difficulty in studying this stack is that this is not of finite type. Only locally of finite type, but the bundles can, when you parameterize bundles or Shtukas, there's this Harder-Narasimhan polygon that can go arbitrarily unstable. So the geometry of moduli of Shtukas near infinity is very complicated. In particular, it's not a bounded moduli problem. Yeah, we can, nevertheless, we can try to define analogues of Kudla-Rappaport cycles. So that's the next construction. So we're going to do it slightly more intrinsically. So the way I learned it from the papers by Kudla and Rappaport is one first constructs divisors, and then by intersecting a bunch of divisors, we get higher codimensional cycles. We can actually start with an arbitrary vector bundle. We can kind of do it in one step. So start with the arbitrary vector bundle on X prime or rank n. Let's consider this special cycle. So I will define this moduli problem, ZER, as classifying the following thing. So first, it will map to the moduli of Shtukas. So it will classify a unitary Shtuka of rank n with R legs. So I'll indicate the legs here. But on top of that, we will give maps from E to each of these FIs. T0, T1, TR, such that this diagram, each triangle is commutative. And the last map will be the Frobenius pullback of the zeroth map. And this makes sense because this E is defined over the base field K. So it's equal to its Frobenius pullback. So tau of T0 is can be viewed as a map from E, again from E to tau of F0. And we require all these triangles to be commutative. This essentially, everything is determined by one map, is T0. And T1 is determined by T0 and etc. But then you go back to tau of F0, it imposes an equation on T0. So it's really the choice of T0 is basically a discrete amount of choice, rather than if you just look at T0, it looks like it's parameterized by some vector space, but the Frobenius equation cuts it down to something discrete. So by definition, this maps to unitary Shtukas by forgetting all the E, or E is part of the data, or E is fixed, but by forgetting the TIs, we get this map. This is not a closed substack in general, but this is not far from a closed substack. It's always a finite unramified map. Okay. So when E is a line bundle, these are really analogues of Kudla-Rappaport divisors. Except when this is literally a divisor when R is 1. Maybe this special case, it's analogous to KR divisors. So again, when E is a line bundle, this dimension is maybe let me say expected dimension. So this I can say in general. So if rank E is n in general, then the expected dimension of this special cycle is, well, expected codimension is m times r. So expected dimension is n minus m times r. So yeah, so this has to be made more precise. So let's look at a kind of a extreme case just to illustrate the dimension of this special cycle is not always well behaved. So we can, according to definition, we are allowed to take all these maps to be zero. That's a kind of extreme case, but that puts no constraint on the Shtukas. So this means for any choice of E, we actually get a copy of the whole moduli of unitary Shtukas inside as a substack when corresponding to the locus where all these maps are zero. Okay, so its dimension, if you just literally take the definition, its dimension will be the same as n times r. Okay, it's not smaller; it's actually bigger. Of course, yeah, this is a kind of a pathological part of it. We can remove it and look at whether the rest of it is well behaved. But even then, if you remove it, there will be less pathological pieces. And somehow there's a whole hierarchy of how degenerate the pieces are. So it's complicated to say. Well, the actual dimension of this stack is not very meaningful, and the expected dimension. The meaning of expected dimension can be made precise by some derived intersection theory. This is developed in a second paper by the three of us. So right now, I'll just concentrate on the case where m is equal to n. This is where the expected dimension is zero.
Zhiwei, if you will put the restriction that the TIs always have maximal rank or are injective or something like that, will then you get the expected dimension?
Still not. Still not.
Okay.
Yeah. So in the case of even in this case, when m is n, we may assume. Yeah. So let me. Yeah, the short answer is still not, but to explain a little bit more precisely, let me introduce some notation. Yeah, so we have a well-defined map from this cycle to Hermitian forms, a set of Hermitian forms, of Hermitian, Hermitian maps from E to conjugate dual of E. Just by by restricting the Hermitian form of Fi on E. Okay, just by restricting Hermitian forms from Fi. It doesn't matter which I you choose because everything is compatible. But let's observe that this target is a discrete space. This is viewed as a discrete set, not as an algebraic, not as an affine space. Okay, because the kind of Hermitian form that we get will literally be defined over original base field, or it's on E. It's not on E base change to any test scheme. This is because we've imposed the Frobenius invariance of T0. So this Hermitian form is really a discrete invariant of points in this special cycle, and therefore it decomposes. Special cycle decomposes according to the induced Hermitian. So let's call this AE Hermitian map on E. This can be 0. A can be 0. It's not required to be non-degenerate. And yeah, so the best case is when A is when little a is non-singular, right? So this, I think, is we hope the behavior is nice. So A is non-singular, meaning it is injective as a map of coherent sheaves. But even in this case, this actual dimension of the RE of A can be positive. So this is again, this is already in the work of Kudla and Rappaport, they had to deal with these non-proper intersections and the similar phenomenon here. That's the whole difficulty of calculation of intersection numbers. Yeah, just maybe, yeah, just to connect back to the KR divisors. If our bundle E is a direct sum of line bundles, then this ZRE from the definition, it's just the fiber product of ZR L1 up to Ln. All these are relative to the Shtuka. As space as stacks. So we can you know, fix a Hermitian map on E, fix some component, and then we get this is a component of the A1, etc. Yeah, all this is completely parallel to the number field case. This is a open and closed in the ladder. So the AI are the diagonal entries of A. And so in order to, okay, so in this case, this is open and closed. In this case, we can define a zero cycle. Can define a zero cycle using this decomposition and with the help of these KR divisors. So we take the intersection product of these cycles over a Shtuka UN, and then, well, the resulting cycle is supported on something with extra components, but we can just restrict to the component we want. This will define a zero cycle on the kind of physical support of this special cycle. So, well, this I'm skipping a step here, which is when E is a line bundle for each of these factors, we can actually make sense of its cycle class, its fundamental class, even those when the only case that needs to be worried about is when A is 0, in which this will not have the correct dimension, but still there is a way to make sense of it. So this at least gives a kind of a definition of a zero cycle on this special cycle, which is expected to have dimension 0. But then, of course, we need to check that this definition is intrinsic. It doesn't depend on how you decompose E into a sum of line bundles. And what if E is not a sum of line bundles? We have to, it would be nice to have a general definition. Okay, so let me just say, well, there is a general definition one can define. A zero cycle in all situations, even when A is 0, this can be defined, and it still has the in the most singular case, it can still be defined. So this most general definition is in the forthcoming paper with Tony and Wei. But when A is non-singular, we can do it in a more elementary way by by picking a direct sum of line bundles that's not isomorphic to E, but almost. So we can allow some discrepancy between the direct sum and E, as long as this discrepancy is disjoint from the locus where A becomes degenerate. So A is a non-singular, means as a Hermitian form on E, it's generically non-degenerate. But at finitely many points, it will be degenerate. So it gives a divisor, degeneracy divisor of A. And as long as you choose this kind of framing, whose difference, whose co-kernel, the support of the co-kernel is disjoint from the support of the divisor of A. And then one can show that this special cycle defined for E is actually open and closed. Well, closed is obvious, but it's also open inside the product, the intersection of these LIs. Open and closed, and we can, we have the zero cycle here defined by the intersection product, and then we just restrict to this open and closed subset. That again at least gives a definition of this zero cycle, even when E is not a direct sum of line bundles. I have not addressed whether this definition is independent of the choice of this framing, but that can be, that is proved in our paper. Okay, so so that's, I think at this point, I can say there is a well-defined number for each non-singular A that is by taking the degree of this zero cycle. So here we really need A to be non-singular, which implies the underlying physical cycle is proper. So zero cycles have a well-defined degree. Okay, so this will be one side of the formula. Okay, so I think I can state the theorem now. So again, let me write the assumptions. Rank E is n, A is non-singular. Permission map from non-singular just means this is the injective map. Then we have this number degree of this zero cycle. The other side involves the Fourier coefficient of Eisenstein series. So let me write some E tilde, some normalized version of Eisenstein series. Fourier expansion is performed at a base point determined by E. Fourier, take the eighth Fourier coefficient, the variable being S, and there is some degree shift. This whole function take the rth derivative at S equals 0. Okay, so this is always there log Q to the R because the variable is Q to the S. Yeah, so here D, well, D just appears here as this number D is the degree of the divisor, this degeneracy divisor of A that measures at how many points A fails to be non-degenerate. Otherwise, so this Eisenstein series is a is an Eisenstein series for U2M, which is normalized. Normalized as there are some zeta factors inserted, such that when S equals 0 is the central point, the center of the functional equation. So Siegel-Eisenstein series. And so let me maybe explain what it means to do Fourier expansion at E. So E for us, yeah, so this is a kind of theorem is already finished, and I'll explain some notation on the Eisenstein side. So E is an element, E is a vector bundle of rank n on X prime. So E can be represented by an element maybe called H in GLN. Well, yeah, that's sorry. So this is the usual description of vector bundles on a curve by double cosets of GLN, of this adelic GLN. So F prime is the function field of X prime. Okay, so to any vector bundle on X prime, I get a well-defined double coset for GLN, and then I can put it. Well, I can pick a representative, so H in GLN of AF, and well, I'll what exactly is, yeah, something like that, conjugate inverse or conjugate transpose maybe. So in any case, I identify GLN of the quadratic extension as the Siegel-Levy in this U2M.
You have n equals m.
Yeah, oh yeah, thank you. This is n. Yes. N equals n. So this is the base point of the Fourier expansion. Okay, so we have this function, this Eisenstein series. We consider it as a what do we call it? B, as a function of B. Okay, so here this is the function for which we're performing Fourier transform. And what is B? B in geometric language is parameterized by extensions, Hermitian extensions of sigma E dual by E. Dual by E. Okay, so this is a strictly upper triangular corner, and it's pointing some unipotent group which parameterizes, whose adelic points parameterize extensions given E as the Siegel-Levy, as the Lagrangian subbundle. We are classifying all unitary or Hermitian bundles that fit into such an exact sequence where E is a Lagrangian. Yeah, so this is some vector space over K where B belongs, and the Fourier dual variable to B is exactly A. That is Hermitian maps from E to sigma to B, E check. Just the usual stereo duality calculation. So, so it makes sense to talk about, so perform the Fourier transform to this function as a function in B, and then take its eighth Fourier coefficient. The variable is still there. So this is the meaning of the right side. Right side of the formula. But it's actually not hard to rewrite it in terms of something more elementary. This is really just a density function. The representation density function, polynomial, for the Hermitian, for the pair E comma A. usually we talk about density of representation density of Hermitian lattice. So just place by place, we have these density functions. This is just a product of local terms. Density Qx S Ex Ax. So at every place x, this is every place of x, we will have a Hermitian lattice by restricting E and A. And we have the density function, which is a polynomial invariable, this Qx to the power minus 2s. And we just take the product. So the result is again a polynomial in Q to the minus s, or 2s. Okay, and this shift is just to make it palindromic. This shift just to, so that the resulting thing is a Laurent series in a Laurent polynomial in Q to the s, symmetric about the constant term. And for that reason, we see that the right-hand side is 0 when R is odd. It's an even function in S. And this is consistent because I mentioned when R is odd, left-hand side is empty. So that's identity is not interesting. So for even R, this is this has content, and in some cases you can work with GUN instead of UN to get formulas that includes odd R. Okay, so I'm running out of time. I want to just to mention two ingredients involved in the proof. One is a formula proved by Chow and Yamauchi formula for density. So, well, strictly speaking, they prove it for orthogonal groups, and Chao Li and Wei Zhang extended it to unitary, to Hermitian lattices. So that's a formula that still it's a little bit complicated, but it's some yeah. So that's one ingredient, and another ingredient is very specific to the function field. Is that when we talk about the Shtukas and the special cycles, hidden in the background is some varieties, some moduli spaces that don't involve Frobenius. So these are varieties where, in their definitions, they involve the Frobenius map. So, for example, they don't make sense over an arbitrary, over a characteristic zero field. But in the background, there's this moduli stacks, let's say bun UN, just classifies unitary bundles. This makes sense over any base. And there's a certain procedure to go from bun UN to the moduli space of Shtukas by basically by adding in a Frobenius, by requiring the object that you classify to have a certain relative position after pulled back by Frobenius. And similarly, for these special cycles, there's also a moduli space we call it M that doesn't involve Frobenius, but you can recover special cycles by applying some procedure to M that's similar to the procedure that you applied to get Shtukas out of bundles. Okay, so these are moduli spaces without Frobenius. And much of the work is to understand the geometry of these moduli spaces. So this is easy to define. This is just classifies a pair consisting of an arbitrary vector bundle, say rank M, on X prime, and a map to a Hermitian bundle. So it's something very natural to consider. We think of this as some kind of Hitchin moduli space and try to understand its cohomology. And its cohomology is related to calculating the degree of this special cycle by some application of Lefschetz trace formula. So the upshot is that we need to understand the cohomology of fibers of a certain map from M to A. M is this M, and A classifies Hermitian maps for E. Now, these are not discrete anymore. It's a moduli space, and we need to understand the cohomology of the fibers. Somewhat miraculously, the cohomology of these fibers are going to match the formula of Chow Yamauchi for these local densities. And this matching they are related by a version of Springer theory for Hermitian torsion sheaves. So that there's a little bit of geometric representation theory involved in the core of the argument that I don't have time to explain. Okay, so I'll stop here. Thank you for your attention.
Great. Thanks a lot. Thanks for the beautiful talk. Any questions or comments?
I'll ask if Steve doesn't have an immediate question. The actual Siegel-Weil part of the construction is in the identification of the Fourier coefficients with the density. I mean, there's no theta correspondence involved in the proof. Is that right?
That's right. So you're asking when there's no lag, everything's just function theoretic. Mm-hmm. Yeah, in that case, we don't do any extra new work. You're exactly right. The work is in the translation between Eisenstein series and this density. Mm-hmm. Mm-hmm.
So in this case, Eisenstein series, the earlier value is like a value or derivative are not zero, right? It's not clear it's zero or not. You take arc derivative.
Oh, the earlier derivatives are not no. We don't make any assumption about the vanishing order. Yeah.
Are the derivatives all supposed to be non-zero? Is there anything like Birch and Swinert and Dyer in this situation?
I don't know.
So what happens like if we don't assume the field extension is ramified? what happens like if we add some ramification, then what will happen?
Yeah, that's a very good question. So, so the core of the argument involves this Springer theory. I think much of the framework still works. The Springer theory will be involve Hermitian sheaves on some ramified double cover. I think it should. Yeah, I think some modification of the argument should work. I haven't really thought about the precise statement. No, but I imagine it's possible to develop an analog. Right.
So is the moduli of H-Shtukas in this case smooth, or it's like not smooth, not even regular, if we add more ramification?
Okay, yeah, that's good. Yeah, so you need to work with some parahoric level structure, yeah, for ramified unitary group, and okay, yeah, I haven't really thought about it. I don't know if my co-authors have comments. That part, yeah, I think that involves some subtlety. So all I can see is when you get to the Springer theory part, it's it doesn't seem to involve much extra work.
Okay, thanks a lot.
We did maybe Zhiwei, you mentioned that we did there's a cheap way to get an odd order, right? By imposing semi-unit factor. So that's some kind of a level structure. So we can get we can get like first order derivative.
Okay.
With actually that case, the modular space is smooth, right? It's still the same singularity.
Yes.
There's nothing. It's actually smooth.
Okay.
Yeah, I was gonna ask about this odd leg thing. Like, what kind of level structures do you impose?
It's really just the same moduli problem. Well, so first of all, it only works when n is odd. So
Right.
n is odd, and then instead of so we just changed the notion of Hermitian bundle. Instead of for the Hermitian form to have values in differential forms, we change it differential forms to some other line bundle on so some other pullback of some other line bundle on the this is a pullback of one form is on the base curve, and we change it to some other line bundle. That's not a norm. Then you get order derivative.
So that's different from the number field case, right? Because in the number field case, you have to do this thing that Ben Howard did. In other words, you have to also add this modular space for CM elliptic curves.
Okay, I'm not familiar with that work. Maybe, I don't know, Wei has some comments about it.
Right, yeah, here it is different, I think, because our bundle E is a Shtukas without a leg.
Right.
And in the number field case, we're looking at elliptical curve, or some elliptical curve. Well, to define divisor, we consider elliptical curve, which in some sense has leg, right? So I mean, the modular of elliptical curve, same elliptical curve. So there is some difference.
I see. Another question is I mean, you took here s equal to 0. Are there other special points?
But those are dictated by this m and n, right?
No, well, what I mean is, what about s equal to 1/2? right? I mean, maybe Steve can say something about
Right.
this. Huh?
Right. We don't know actually, right? What happens s equal to half, right? 1/2.
Ah. Is it related to the? Yeah. Okay.
No, but Drew, maybe we
I
had
suppose
a.
in one sense, this is some analog of just the fact in the classical case, we often concentrate on the central critical value, the central value of the incoherent Eisenstein series, and look at the leading term and so on and so forth. So that by incoherence, we know that it's zero there, and we look at the derivative, which would be the leading term. But in fact, if you look at these things about these Eisenstein series that I've in my business, it's often true that if the dimensions are different, you end up with a non-central point, and then the value and the derivative of the Eisenstein series may have some geometric meaning. And so, for example, in my paper with Rappaport and Yang on the case of Shimura curves, we have an Eisenstein series of weight 3/2, but we end up with the critical value being at s equals 1/2. You know, again, the functional equation is usually s goes to minus s. So this is not the center. It's what might be called the Tate point. And then motivically, it would be the Tate point. And so in some sense, then there, the value is non-zero, and it's given by the degrees of the cycles, which is it goes on only on the, so these are zero cycles on a Shimura curve geometrically. And so then the value of the Eisenstein series there is simply the degree. So some class numbers counting the number of CM points on a Shimura curve. And it's the next term in the Lorentz expansion. And now you have to be very careful about how you normalize the Eisenstein series, because since the value isn't zero, if you multiply by some function of s, you end up mixing in some piece of the value. So you have to really take the right normalization. But then the next term in the normalization is the points are now the Faltings heights of those CM points, right? Essentially given by the Faltings heights of some CM points, where now it's not, the CM point corresponds to a place where your abelian surface, where on a Shimura curve, is really isogenous to a product of a CM elliptic curve with itself. And now you see the Faltings heights. So you see both terms are non-zero in general. So this is somewhat analogous to what you're saying here. In other words, you don't see a Birch-Swinnerton-Dyer type phenomena. You know, you're not looking at the leading term anymore. So maybe it's more subtle or less subtle, I don't know. But of course, here you dig even deeper, right? And I don't know what the analog of that is. I mean, but in any case, in the classical situation, there are situations where you have two values, or two s naught is a half in this case, and both the value and the next term have some geometric interpretation in terms of arithmetic geometry. But of course, we don't know what the next term after that is in the number field case. That's a complete mystery. So anyway.
But here I think there's also a candidate. We also have a candidate for some tautological class, some Chern class of certain tautological bundles. So it's likely those off-central value might just be sometimes, I mean, has something to do with the degree with respect to those tautological bundles. So, but we haven't got any clear answer to that.
I think here might be like because I'm working on non-singular, so you get this derivative, exactly this arch derivative. Suppose A is a singular, this Eisenstein series is not the product of a number of coefficients. It might be maybe sum of the two things, and each one of these actually related to a lower dimension Eisenstein series derivative at slightly away from the center. That's what we do in a classical. This probably also a similar case that showed up. As like which makes sense if we go like the m is m-1, right? Then you probably got what you got, it will be you still get the degree, and you also want to in the section with the tautological bundle, then you will get the derivative on the not as the center, but the center away from the center. Shift a little bit because of this S0 is come from m minus n, something like that.
Yeah, we have a general definition of these cycles of the correct degree, including all possible n, all a's, including a0, for example. And it has some, yeah, it will be a sum of many terms indexed by the possible kernels of E mapping to F. Yeah, so it looks similar to how this constant term of Eisenstein series decomposes.
I mean, I think the example that Tonghai mentioned is actually the same example that I mentioned, and that is that in our book, when we're looking at the central derivative of the genus 2 Eisenstein series associated to zero cycles on the Shimura curve, arithmetic zero cycles, so that's an incoherent Eisenstein series. So the non-singular coefficients have a product formula and an interpretation in terms of derivatives, et cetera, but the singular coefficients don't have a product formula. And as the rest of that Eisenstein series doesn't vanish because there's a product with one factor in the product vanishing, it vanishes in a collection. So now what you see is there's some when you take those the singular part of the Fourier expansion, what you end up with is Eisenstein series on smaller groups, but now there's a shift in the S value. That's what Tonghai is referring to. And so what happens is that other part in the book, the Eisenstein series that I mentioned of weight 3 halves comes in and on SL2 for the Shimura curve, not SB2, on SL2. So now you're away from the center, but that comes in, and its functional equation is what's called causes the vanishing of those contributions in the incoherent guy at the center. So there's some functional equation relating the two pieces, and they cancel in their contribution to the genus 2 guy. But you see, it suggests that maybe to get these off-center points, just as Tonghai is saying, you need to look at this more singular guys, and that somehow that complication about indexing by kernels and so on and so forth will lead you into some slightly more general type of Eisenstein series on smaller groups. But now there's an S shift because of some row shift in the constant term calculation, which will naturally give you some way of seeing perhaps these more general situation in a smaller rank group, if you see what I'm saying. So maybe Tonghai is really explaining what you could try here to see what these more general off-center points could look like.
So maybe a related question is, you take this to the extreme where you take the constant term of the Eisenstein series. I guess you would expect that you get some higher derivative product of zeta functions, or in this case, abelian functions of quadratic character. But some of the factors are shifted. So the constant term really just see higher derivative zeta function at very far points, right? Very far from the center.
That's right. Yeah. Okay. Yeah.
So somehow all that information is sort of packaged at S equals 0, but because of the singularity, you're moving the critical value is moved away from the center. And so you see actually more information there. One would like to ignore the singular part, but in fact, in some sense, the singular part is maybe very interesting. And there's more information there, not less, somehow.
Right.
The harder.
So we have a trivial case. The n equal to 1, right? N equal to 1, we can compute the constant term. So
yeah, so you can do tiny now.
Right. Yeah, the tiny case. Right?
Like get this omega hat stuff square.
Pseudo speed, right? So
Yeah.
the degree of a certain bundle. Yeah.
Yeah.
Term class of certain bundles. Right.
Other questions or comments? If not, let's thank Zhiwei again.